Hello, dear students. Welcome to the channel, and once again, welcome back to the Signal and System playlist. In this playlist, we are exploring the very basics of signal and systems. Initially, in the beginning of the playlist, we have seen what is a signal, we have seen what is a system. Um, then we have explored various kind of signals. We have seen continuous time signals, discrete time signals, analog signals, digital signals. We have explored periodic and non-periodic signal. We have seen even and odd symmetry of the signals. We have also seen power signals and energy signals. We have also seen uh, what is a random signal and what is a deterministic signals. Right. So we have explored these many type of signals till now, and today we are going to explore one more important type of signal. It's called absolutely integratable signal, and the very base of this is uh, lies under the concept of bounded signal and unbounded signal. So if you will understand the concept of bounded signal and unbounded signal, it will be very clear to you to understand the concept of absolutely integratable signal. Okay, and after that, the classification part of the signals will be over, so we'll be discussing some very important signals which we normally use while doing any kind of signal processing operations. Okay, so without further ado, let's get started on absolutely integratable signal. If you have not explored the uh, previous video, or and if you want to know more about different type of signals, you want to explore more in the field of signal and system, so please watch the previous videos. You will be seeing the link of the previous videos and the link of this playlist on the I button on the top right hand side corner of this of your phone. So I assume you have seen all those videos, so let's start the absolutely integratable signal. Okay, so the term absolute integratable is applicable to a function of a continuous variable. Okay, if my function if my signal is having a continuous value, then the term absolutely integratable is applicable. Okay, you know what does that means, that discrete time signals are not part will not be part of that, right? Now as we are already ruled out the possibility of discrete time signal to be absolute integratable signal, let's consider a continuous time signal. Then let's think of a time signal, continuous time signal of x of t, and what we will do, we will take its absolute value and then we will integrate it with respect to t. Okay, first we will take its absolute value and then we will integrate it with respect to t. After that, what we will do, uh, okay, before going to that, limits, right? What will be the limits of this integration? So the limit of this integration should be all possible values. Okay, all possible values of t, and in this case the t is my real time variable. Okay, so after doing that, what we will do, we will plot the graph of t from minus infinity to plus infinity. Okay, so basically we are plotting the graph of t over the entire time span. Okay, and if the value of this integration is finite number, then we will call this signal absolute integratable signal. Okay, so if you are not very much clear about it, if you are still having doubts, this will make you clear about it, that let's say we have a signal, let's say we have a signal which is very strictly time limited. Okay, which is shown here on the left side. Let's take this signal, rectangular pulse. Okay, So it is a strictly time limited signal. Agree or not? See, it is going from minus t by 2 to plus t by 2, and except for this, between these value, it is having some magnitude. And after minus t by 2, it is having 0, and after t by 2, it is also having 0, right? So it is strictly time limited signal. Agreed, right? So what we will do, we will take the integration. Okay, we will take the integration of this signal over the entire time span, which means we will take the integration of minus t by 2 to plus t by 2, right? Because except for these values, it is having 0. Okay, so righteously, what should we do? We should take a limit of minus infinity to plus infinity. Okay, so we will take the limit of minus infinity to plus infinity. But as the values accept as this signal, as my rectangular pulse signal is only having the real values between minus t by 2 to plus t by 2, we can only take those only take that part in consideration for integration, right? Which makes this signal your bounded signal, right? It is, its limits are defined minus t by 2 to plus t by 2, except for that it is 0. Everywhere else it is 0, right? And because of that, we can say that this signal is absolute integratable signal. Okay, because firstly it is continuous time signal. Okay, yes, it is continuous time signal. If it is continuous time signal, then check if this signal is a bounded signal or not a bounded signal, right? To do that, what we will do, we will take limit of integration, and we will take the integration from minus infinity to plus infinity, and we will check the result or the value of that. If that value is finite, which is in the case of all the bounded signals, then my signal will be called absolute integratable signal. Now let's consider another case. Look at the image you are seeing on the right hand side. Okay, can we say that this signal is time unbounded, right? This signal is not bounded by time, right? How can we say that? Say at t is equals to infinity, uh, t is on the x-axis, you can see here. So when my t approaches infinity, can you tell me what will be the value of this signal, right? Because it is rising, 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 and it will keep rising. So you only possible guess you can make about the value of your signal at t equal to infinity will be your signal will also be infinity, right? But what was this case here for this rectangular pulse at t equal to infinity? You can confidently say that value of my signal will be 0. Why? Because my signal is bounded between minus t by 2 to plus t by 2, right? But you cannot say the same for the time unbounded signal, this signals. And hence this signal is called is called is it's not called an absolute integratable signal. Okay, or you can also call it not absolute integratable signal. Okay, so the property of signal, the bounding property, if my signal is bounded signal or unbounded signal, decides if whether my signal will be an absolute integratable signal or will it be not absolute integratable signal. Okay, so this ramp function will be non absolute integratable signal. So those are the all the types of the signal which we have explored till now, including the previous lectures which we have discussed, where we have discussed all those kind of different kind of signals. Remember continuous time signal, discrete time signal, and all those kind of type of signals. Okay, so that was it about the classification of signal. Now let's discuss about few very popular, or you can say few very famous signals, or the signals which will be very helpful to you during you perform any signal processing operations. Okay, so first is unit step signal, and it is the most common signal. It is a few of the most common signals which you will come across, because uh, you will see this signal multiplied with almost every signal in the beginning of the signal processing. Okay, Because what does this signal do? To learn that, let's see the definition of this signal. So what does the definition of the unit step function says? So it says the unit step signal has amplitude of 1 for positive values of independent variables. Okay, and it has amplitude of 0 for negative values of independent variable. Okay, what does it means? It means if you try to plot a graph like this, so all the values on the right hand side of my y-axis, what it will have, all the values on the right hand side of my y-axis will have amplitude 1. Okay, all the values on the right hand side of my y-axis will be having amplitude 1, and all the values on the left hand side of my y-axis will be having amplitude 0, right? That was for my continuous time signal. Okay, what will happen for the discrete time signals, right? Discrete time unit step signal will look like this. The concept will again remain the same. So the value will be 1 for all the samples on the right hand side of my y-axis, and for all the samples on the left hand side of my y-axis, the value will remain 0, right? So and the amplitude will be 1. Okay, amplitude will be amplitude will be 1 for all the samples collected on the right hand side of my y-axis, and amplitude will be 0 for all the samples collected on the left hand side of your y-axis, right? So that is your unit step signal. You can mathematically represent this unit step signal as u of t is equals to 1 for all the t greater than or equal to 0, which means on the right hand side of y-axis, and 0 for all t less than 0, which means on the left hand side of my y-axis, right? And always remember, uh, the amplitude or the value of my unit step signal will either be 0 or either be 1. Okay, it will not go in between 0 or 1. Okay, it will either be 0 or it will be 1. It cannot be zero point 0.5 or something, except you multiply it with zero point 0.5, right? And how do we represent unit step signal in discrete time signal? How do we represent the unit step signal as a discrete time signal? We write u of n is equals to 1 for all n greater than or equal to 0, and u of n is equals to 0 for all n less than 0. Same ways as we represented continuous time signal, but here we are taking samples, right? And if you want to represent it in sequential form, then you can also represent it like that, that this arrow indicating origin or 0. Now what is the significance of unit step signal? Okay, so normally I've told you that most of the times when you take signal processing operations, you will be considering discrete time signal, right? So discrete time unit step signal is sampled version of continuous time unit step signal, right? Or you can learn it only by looking at both the images, right? We are doing, we are taking sample at t equal to 1, then we are taking sample at t equal to 2, then we are again taking sample at t equal to 3, right? So what is it? It is sampled version of continuous time unit step signal. And then unit step signal is generated when DC supply is applied to the circuit. Okay, and unit step is generated when switch is close at t equals to 0. Okay, when my switch will be closed, at that time unit step will be generated, right? Because remember how does DC supply works, right? DC supply, what is the frequency of DC supply, remember? So it will be straight line DC supply. Now let's come to another function, interesting function, unit impulse or delta function. So this function is called different for continuous time and discrete time. In continuous time we call it unit impulse signal, and in discrete time we call it unit sample signal. and it is having different definitions for both continuous time and discrete time signal. So let's see first for the continuous time. So what will happen? The definition says the area under unit impulse approaches 1 as the width approaches 0. Thus it has 0 value everywhere except t is equals to 0. Okay. So in the graph, come here, see the graph. In the graph it is showing the value everywhere there is no value, which means value is 0. And at t equals to 0, see there is some value. Okay, there is some value, but the value here, as it is a continuous time signal, you may ask that why am I seeing a sample? It is not a sample. Okay, it is not a sample. What actually happening, that width of my signal is approaching almost 0, right? The width is almost 0, and the area under this under the signal will be equal to 1. Okay, and if my signal possesses this kind of property, we call it unit impulse signal. Now let's see about what happens with unit sample signal, which is in discrete time. Okay, so amplitude of unit sample is 1 at n equals to 0, and it has 0 value at all other values of n, right? It is pretty much easy and clear, right? When your n value of your n is equal to 0, at that time your signal is having amplitude 1, and except for these this one value, everywhere else it is having value 0, which you can see via its mathematical expression as well, right? See, for unit sample signal, del n is equals to 1 for n is equal to 0, and del n equal to 0 for n does not equals to 0, right? You can represent it in sequential form like this. And if you want to see the mathematical expression of unit impulse signal, which is in continuous time signal, so we will do, we will take the integral again, minus infinity to infinity, del t into dt, and it will be 1. Remember, by doing this, what we are doing, we are calculating the area, and what this definition says, area under unit sample approaches 1, so the area will be 1. And at t equals to t tends to 0, delta t will be uh, this much, the delta t will be 1, as equal as this integral. And for the delta t equals to at t does not equals to 0, my delta t's value will be 0. Okay, so for t does not equals to 0, my unit impulse signal will be 0. Now what is the significance of this signal, right? What is the significance of unit impulse signal? So firstly, what we have seen just a moment ago with unit step signal, we have seen that discrete time unit step signal will be a sampled version of my continuous time unit step signal, right? But that will be not the case here. The unit sample signal, or let's call it del of n, let's call it unit sample signal del of n, and unit impulse signal del of t. It will save us a lot of time. So del of n is not a sampled version of del of t. Okay, firstly know that del of n is not sample version of del of t. They both are different. What is the difference, you may ask? The difference is here, see what it is, what is it saying? The area under the unit impulse is approaching 1. Okay, the area here is approaching 1, and what is happening with del n? With del n, the amplitude is 1. Okay, at del n we are having amplitude 1. Okay, then where is it used? So this unit impulse, or call it unit sample, both of them are used to determine the impulse response of my system. If I want to determine what is the impulse response of my system, then I will be using unit impulse or unit sample signals based on my signal, and based on my requirement. Okay, then the frequencies of these signals. So both of these unit impulse or unit step function contain all the frequencies from minus infinity to plus infinity. As you can see, the value of amplitude is 0 except for x is equals to 0, right? Now let's come to the third type of signal. It is called exponential signal. So what will happen with exponential signal? Again, let's see the definition. What does it says? It says it is an exponentially growing or a decaying signal. Okay, and this decay and growth of my exponent will depend on the value of my a, or a and b, both of them are variables. So before seeing graph, I wanted to see the mathematical expression of the same. So what does the mathematical expression of my continuous time real exponential signal says? By the way, these exponential signal we are going to discuss only about the real exponential signal. We are not going to discuss about the imaginary part of that. In order to discuss the imaginary part of that, we have to go into the complex numbers. And right now I'm not sure if you all are that much familiar with complex numbers, so I'm not including them right now. But if you want me to do, please mention it in the comment section below. I will making a separate video on it if you want to. But for now, let's focus on continuous time real exponential signal. So we represent it with the mathematical expression given as x of t is equals to b e of a into t, b e raised to a into t, and here both b and a will be my real values. Okay, both of them will be real values. Now what will happen if the value of my a will be less than 0? Okay, so when the value of my a will be less than 0, my exponential signal will be a decaying exponential. Okay, it will be decaying exponential, it is coming down, see. And what will happen my when the value of my a will be greater than 0? At such time my exponential will be a rising exponential, see, it is rising from here. Okay, it is increasing here. Now let's see the discrete time real exponential signal. The mathematical expression will be a little bit similar to the continuous time real exponential signal. We can say x of n is equals to b r raised to n. If uh, we say the r will be e raised to a, then x of n is equals to b e raised to alpha into n. R is equals to e raised to alpha. Apologies. R is equals to e raised to alpha. Then x of n is equals to b e raised to alpha n. And again here b and alpha both are real. And similarly, how we plotted for my continuous time real exponential signal, we will plot for discrete time real exponential signal. What will happen here? Again, last time we were discussing if my value of my a will be less than 0. Here we will be discussing the value of my r. Okay, so when the value of my r will be between 0 and 1, okay, when it will be between 0 and 1, at that time I will be getting this decaying exponential. And at the moment when the value of my r surpasses 1, at that time I will be getting this rising exponential. Okay, I will be getting this rising or growing exponential. Okay, uh, and again please note one thing, that here we were discussing if a's value will be less than 0, but here we were discussing r's value. And also note that r is nothing but e raised to alpha. So here we were only discussing about the power which my e had, but here we are discussing about the whole term e raised to alpha. Okay, then let's come to what is the significance of this this exponential signals. So the significance of this signal will be, firstly, for the continuous time real exponential signal, what will happen? The charging and discharging of a capacitor can be represented by continuous time exponential signal, right? When my capacitor is discharging, you can see this pattern, both of these patterns. When my capacitor is either charging or discharging, at the discharging you will see this decaying exponential, at the charging time you will see this rising exponential. Okay, you can demonstrate the charging and discharging of a capacitor with the help of continuous time real exponential signal. Except for that, you can show the current flow through an inductor with the help of that. And except for that, you can also show the radioactive decay of various components. If you have studied, if you are into uh, chemistry, if you are into the modern time elements uh, which are getting introduced in time and time being, if you are into uh, if you are into uh, excursion of uranium and thorium like elements, which can produce a tremendous amount of energy for us. So in the radio in such kind of chemistry, you will see radioactive decay. Except for that, if you are into extraterrestrial objects, if you want to detect their age and all that, in that we also use the we use radioactive decay. So for that we can use that. And the discrete time real exponential signal, where do we use it? So we can show the population growth as a function of this signal, right? With this growing exponential signal, we can demonstrate the population growth as a function of generation, right? We can take the samples per 10 years and we can show it, right? And the return on investment as a function of a day or a month or a quarter, right? We can also show the return of an investment as a function of these growing or decaying, right? So these were some of the very useful complex and exponential sinusoidal signals. Except for these, let's come to the system part. The signal part will be end here, not will not end, but let's keep it keep it on a hold for some time, and let's get to discuss systems, because I also want to discuss different types of systems, right? So before going to that, I quickly want you all to remind what is a system again. In case you have forgotten, let's come here. What is a system? So system is a set of elements or functional blocks that are connected together. Okay, there are set of elements or functional block that we connect together and produces an output in a response to some input signal. Okay, it is a set of elements or a functional block that are connected together and produces an output in the response of an input signal. And what were the examples of my system? So you can consider an audio amplifier, or if you have any antenna, transmitter, receiver signal, you can consider your TV set, you can consider a radio or your machines, engines, everything is a system. Okay, then we have seen the relation between signal and system, what is analogy we were having, right? So every system has one or more input, which we call excitation, and every system has one or more output, we call it response. Then let's come to what are the classification and properties of systems. So firstly, discussing the classification. So basically there are two types of systems. One is called continuous time systems and another one is called discrete time signal. uh, it is very basic if you understand what is continuous time signal and continuous time what is continuous time signal and what is discrete time signal. So the continuous time system mostly deals with the continuous time signals, so it handles the continuous time signals. And discrete time system is a system that handles the discrete time signals, right? Pretty much self-explanatory over there. What are some examples? So again, we have mentioned the examples of continuous time systems and discrete time systems. So okay, I beg your pardon for the disturbance. So let's get back to continuous time signals and discrete time signals. So what are the examples of some continuous time systems and discrete time systems? So for continuous time systems, we are having analog filters, we are having amplifiers, attenuators, right? Different types of analog transmitters and receivers, antennas, analog antennas. We call them all continuous time signal. And what will come in discrete time systems? So all of your computers, your mobiles, your microphones, printers, shift registers, any kind of memories. By memories I mean RAM, ROM, EEPROM, all kind of SSD, all kind of memories, right? So all of them falls into the category of discrete time systems. Okay, so from the next we will be discussing the properties of different kind of systems. This lecture I'm keeping till here, and most probably the next lecture will be the last lecture of the first chapter, and the first chapter will end there. So if you have any doubts in this lecture series, or if you have any queries related to the this video, feel free to mention in the comment section below. If you have any feedback or anything regarding channel or anything, everything is welcome. So feel free to mention your thoughts in the comment section below. And if you have any suggestion, everything is welcome, so please mention it in the comment section below. And I will be seeing you in the next lecture. So till then, goodbye and take care, and thank you very much for listening.